activity. So that's the take home. Those of you who want to leave, I'll try to now provide evidence for that. So the evidence for dynamic role as an early regulatory enzyme in GTP hydrolysis is actually quite extensive. First of all of the GTPase and assembly defective uses that we and others have generated in Dynamin over the past 10 or 15 years block early stages of vegetable, not late stages. Chemical inhibitor, Dynamin, which is a non-competitive GTPase inhibitor identified by Tommy Kirkhausen, also blocks early stages of vegetable. As I told you, mutations in GED that impair assembly-stimulated GTPase activity accelerate these early stages of formation. Second class of mutations in GED that were identified by Drosophila genetics as suppressors of the Shibiri phenotype, so-called sushi mutants, suppressors of Shibiri. These mutations in GED rest in second site mutations in the GTPase domain, which shows that the GED activity negatively regulates dynamic function. We'll come back to these a little bit later on in the talk. And finally, recent studies in the arXiv, which I'll show you the data from, show that Dynamin's basal GTPase activity controls the turnover of aborted coded KIT intermediates. So this work that I'll take a moment to tell you about is work by Marcel Metlin, a postdoc in my lab, in collaboration with Dina Loher, a postdoc with Gaudi Danuser, who was within a script, and Gaudi has since moved off to Harvard heaven. This is total internal reflection fluorescence video microscopy of fluorescently labeled BFC-labeled class and light chain dynamics in a BSC1 monkey endothelial cell line. And what you're looking at here is with the TURP, we can illuminate only the bottom 100 nanometers of the cell, and we don't illuminate any of the fluorophores deeper in the cytosol. So in this way, we can monitor events right at the cell surface. It's ideally suited for monitoring plasma-mediated endocytosis and other events at the cell surface. Claire Waterman helped us set this up when she was at the grip. Anyway, what you're seeing here are coated pits that form and pinch off from the cell surface. And as you look at these movies, I was struck by the heterogeneity of it. There are ones that come and go very quickly. There are ones that hang around a little longer. There are very bright, intense objects, and there are dimmer objects. And so, when I looked at this movie as a biochemist, I was a little disturbed, in a sense, by this heterogeneity, because as a biochemist, by analogy, we tend to take a mixture of components, a mixture of cells, a mixture of events at the plasma membrane, and put them together into one blender and end up with something akin to a tropical fruit smoothie. Well, in fact, so I, in a sense, as a biochemist, have been studying tropical fruits. And there may not even be such an entity as a tropical fruit. We study as biochemists the average of events. And in that averaging of all events, we may or may not lose sight of reality. And so our goal with this new assay was to capture and quantify the heterogeneity of events, and then to define the functional and molecular basis of this heterogeneity, and most importantly, to exploit it as a source of new mechanistic insight. So in order to do this, we needed a fully automated, unbiased way to track all of these events, and to establish a complete inventory of trajectories by click. And hence, we collaborated with Gaudi Danuser, Dina Loher, and Harout Zakaman from their lab, who had to deal with this problem of tracking coded pits. The problem is density, their heterogeneity, and the low intensity of the object, and also the fact that they might temporarily disappear because of unevenness in the scale or the proximity. And if you systematically lose sight of something and then gain it again, and you don't fill in those gaps, then everything's going to look like it's short-lived. And so the mathematics for this problem comes from astronomy, where astronomers will look up in the sky during the night and see all these stars of different brightness and heterogeneity and twinkling, and then have to go away for the day and come back the next night and figure out which star is which. So there is mathematics to do this, and it needed to be modified, but Haluk Jackman and Gauss and Dina did this in a way that allowed them to spatially and temporally globally optimize and track all the images, including this all-important method of gap closure. When we detect and track and give trajectories for all these objects and cross the finish line, it's now important to apply statistics to interpret what this heterogeneity is telling us, and that was done with Bayesian information criteria. So what you see here is the analysis, statistical analysis, I don't have the end here, of roughly 50,000 endocytic events taken from 24 different cells, 24 different movies, long and short movies, and trying to capture all of this heterogeneity. And what we see is that there are three populations statistically of the dynamic behaviors of these coding kits. Two short-lived populations which we ascribe to as abortive events with lifetimes of 5 and 15 seconds, and about half of the coded kits have longer lifetimes that we were able to ascribe as productive events leading to coding deficit. We then took this new assay and we did a dynamic knockdown, not a complete knockdown, just about a 50% reduction. And I think this is important because we want to create hypomorphic effects. We don't want to completely kill endocytosis. We want to have a small effect and use a sensitive assay to pick it up, so we can get more, rather than the potential of feedback, inhibition, and other indirect effects of strong dominant negative. So with a 50% knockdown of dynamin, as we expected, as I told you earlier, dynamin is controlling the rate of depth of vesicle formation, and the lifetime of these productive coded kits increases quite significantly. And this lifetime can be rescued, in fact, it can, by rescue with the RNAi resistant dynamin wild type. What was unexpected is, in addition to these effects on the productive population, we also found that knockdown of dynamin caused an increase in the lifetime of these abortive coded kits. So this suggests that dynamin was in part regulating the turnover of these early endocytic nucleus. So from this and a lot of other data that I don't have time to go into, published in these two papers last year, we are proposing a conceptual framework in which to think about the GTPase and its regulation of endocytosis, and which we're suggesting, that dynamin functions to monitor an endocytosis checkpoint. So the basal GTPase cycle of dynamin is controlling this checkpoint, and data I haven't had time to show you, and input into this basal GTPase activity, and actually the dynamin propensity to self-assemble are co-proteins, factors that recognize membrane curvature, factors that regulate cargo, that provide input into this checkpoint as a decision is made whether to abort early non-productive events or to continue on a maturation pathway towards formation of coded vesicles. So we are now busy trying to probe the mechanisms and the input into this endocytosis checkpoint as a framework for our thinking.
and much, much more work needs to be done. But looking at this idea of Dynamic as a checkpoint regulator, as a control of these abortive events, it reminded us of data that's out there for the SAR and ARP CPCs that control COP1 and COP2 vesicle formation. I think, in fact, Jennifer's work showed that the ARP was turning over more quickly than the coat proteins at the Golgi. And in fact, it's now known that there are abortive events in COP1 and COP2 vesicle formation, and that the stability of a coat moving through maturation is dependent in part on the gain of curvature and the assembly of coats and the recruitment